Materials are often placed in service at elevated temperatures and exposed to static mechanical stresses. For example, the turbine blades in the jet or parts of the steam generators. So deformation under such circumstances is termed creep. Creep is a time-dependent and permanent deformation of materials subjected to static stresses at elevated temperatures. It is often the limiting factor in the lifetime of a part. For metals, creep becomes important only for temperature above 40% of T sub m, where the T sub m is the absolute melting temperature. So in other words, this creep failure happens at a higher temperature or at a temperature that is higher than the room temperature. And the fracture induced by creep is termed as stress rupture. A material can be considered failed by creep even if it hasn't fractured. So depending on the magnitude of the applied stress and its duration, the deformation may become so large that a component can no longer perform its function. For example, creep of a turbine blade will cause the blade to contact the casing, result in the failure of the blade. Here are a couple of creep failure examples for the component being used at elevated temperatures. In steam turbine power plants, pipes carry steam at high temperatures and pressures, so creep failure can happen for those pipes. In jet engines, temperatures can reach up to 1400 degrees Celsius and initiate creep deformation in even advanced design-coated turbine blades. And the creep rate of hot pressure-loaded components in a nuclear reactor at power plant can be a significant design constraint, since the creep rate is enhanced by the flux of energetic particles. Therefore, it is crucial to understand the creep behaviors of materials. In a creep test, the specimen is subjected to a constant load or constant stress. It doesn't change with time, indicating it's a constant value or a static stress. And also, the temperature during the test is maintained at a constant value, and usually it's an elevated temperature, higher temperature than the room temperature. And during the test, the deformation of the material is measured or the strain is measured and plotted as a function of time. So in this case, we have the creep strain, which is the change of dimension, change of length over the original length, which is a dimensionless value plotted against the time. So upon application of the load, there is an instantaneous deformation as indicated in this figure here. And this deformation is almost elastic deformation. The resulting creep curve consists of 3 stages. The first one is the primary stage, and second one is the secondary stage, and the last one is the tertiary stage. And each stage has its own distinctive stress time behavior. For the primary stage or primary creep, the slope decreases with time. And the slope is also the creep rate, which is the change of the creep strain with time. So is the creep rate. Creep rate decreases with time during the first stage. And second stage, this portion is almost a straight line, which means the creep rate is constant. And this is the steady state creep stage. The last stage, the slope increases or the creep rate increases during the last stage. which indicates an acceleration in the creep rate. And until the fracture happens or the specimen fails at the rupture point, where the time corresponding to the rupture is the rupture time, T sub r. Let's take a look at stage 1, the primary creep stage. And during this stage, the slope or creep rate decreases with time. And this is caused by string hardening, meaning the deformation becomes more difficult as the material is strained. Is the same idea as the cold working. Because of cold working or string hardening will increase the density of dislocation. Therefore, the dislocation will hinder the movement of each other, make the plastic deformation more difficult to happen. For the secondary or steady-state creep, the creep strain and time has a linear relation, so which means the creep rate is constant. And we can get the creep rate using any 2 points located on this line, and creep rate we have epsilon sub s dot, and this s means steady state, and dot notation means this is a rate. So this rate equals to the change of epsilon over the change of time, and we can get the creep rate during the secondary creep, and this is also the creep rate for a given material. The secondary stage lasts the longest among all 3 stages. The constant creep rate is caused by the balance of string hardening and thermal softening or annealing. So we learned annealing after the cold working, because after cold working, the strength of the material will be increased, but the ductility will be decreased. By doing annealing, the ductility of the material will be restored, because annealing will decrease the number of dislocations, while cold working or string hardening will increase the number of dislocations. So when there is a balance between the increase and decrease, the creep rate will be a constant value. For the tertiary creep, the creep rate increases with time until failure, and this ultimate failure is termed as stress rupture. The increase in the creep rate is caused by necking, grain boundary separation, formation of internal cracks, cavity, and voids. And all of this will lead to a decrease in the effective cross-sectional area and increase in the strain rate. From the creep test, we can get 2 important creep parameters. The first one is the creep rate, which is the slope of the steady-state portion of the strain time curve obtained from a creep test, or the secondary creep portion, the linear portion. So the creep rate is denoted by epsilon sub s dot, which is the ratio of the change of strain over change of time, or this is the slope or creep rate for the steady state portion of the strain time curve. So this creep rate is the engineering design parameter that is considered for long-time applications, such as a nuclear power plant component that is scheduled to operate for several decades. And the failure or too much strain is not an option for those components. Now, in those cases, we need to refer to this creep rate and to choose the right material. Another parameter is the rupture time, T sub r, which we also showed from the earlier graph. It's the time required for failure, or it's the time at the ultimate failure in a creep test. So this rupture time is the dominant design consideration for short-life creep situations. For example, the turbine blades in military aircraft or rocket motor nozzles, those components need to be replaced after a couple of years, and we need to know how long does it last before it fractures. Then we need to replace it before this time T sub R. Both temperature and the level of the applied stress influence the creep characteristics. At a temperature substantially below 0.4 or 40% of the molten temperature, and after the initial deformation, the strain is virtually independent of time, which proves that the creep only happens at an elevated temperature, and this temperature typically is above 40% of the absolute melting temperature of the material. And now we can see by changing or increasing the temperature or the applied stress, the steady state creep rate or the slope increases as well. So the steady state creep rate increases with increasing temperature and applied stress. The rupture time or rupture lifetime decreases with increasing time and applied stress. So this is rupture time for the maximum temperature and applied stress, and second largest has rupture time which is longer than the first, and the smallest or lowest temperature and the applied stress corresponds to longest rupture lifetime. And something else is the instantaneous strain, which is the elastic strain when we just apply the load to the material, increases with increasing temperature and the applied stress. We just mentioned that the creep rate increases with increasing temperature and the applied stress. So the relationship between the creep rate, the temperature, and the stress can be described using the following equations. The creep rate epsilon sub s dot equals to C, which is a material constant, times sigma to the power of n, which sigma is the applied stress, and n is also the material parameter, times exponential of negative q sub c over RT, where q sub c is the activation energy for creep. It's also a material parameter. So this equation or relation looks like a little bit complicated, and we cannot see directly what is the relation between the creep rate and temperature and applied stress. But if we take the logarithm on both sides of the equation, we will have the log creep rate equals to log C minus QC RT, then plus n times the log sigma applied stress. So now it's clear to us that we can plot or this creep rate in log scale and stress in log scale follows a linear distribution if we keep the temperature T at a constant value, because C, Q, C, R, all of those, and N are constants. So we can change the temperature, but we can choose different temperature values and keep that temperature value at a constant number and to plot the corresponding log creep rate versus log stress. So, for example, this is the strain rate or the stress versus steady state creep rate for a low carbon nickel alloy at 3 different temperatures. So first we take the creep test at 427 degrees Celsius. We get a set of data and plot the corresponding log creep rate versus the log applied stress, and this is the line we get. And then we change the temperature to another value, which is 538. We do another plot, and lastly we increase the temperature furthermore to 649 degrees Celsius. We get another line. So from the three lines, we can see that if we keep the stress, applied stress, the same, at the same value. For example, here, applied stress, and we can see when the temperature increases, the strain rate increases as well. So at temperature 427, this is the corresponding strain rate. But for the same stress level at 538, the corresponding strain rate is over here. So clearly, this point is bigger than at a lower temperature. So that's why we say strain rate increases with increasing temperature. Same idea for the increasing applied stress. If we increase the stress to a higher level, if we just compare the same temperature like at 427 degrees Celsius, now the higher the applied stress, the higher the strain rate. The dependence of rupture time, T sub r, on temperature and applied stress can also be described by a very similar equation. Rupture time, T sub r, equals to K instead of C now. K is the material constant as well, times the applied stress, sigma to the power of m, which is the material parameter, times exponential of Q sub r over RT, where Q sub r is the activation energy for rupture, which is also a material parameter. The most important creep property that can be obtained from the creep test is the time to rupture, T sub r. However, in some situations, for some given stress level and temperature, the time to rupture is on the order of years, which means it takes years for the specimen to finally rupture. So in those cases, it is impractical to collect the creep data in a lab. So one solution to this problem involves performing the creep tests for a shorter time of period and at a comparable stress level, and then making a suitable extrapolation to predict the creep rupture lifetime T sub r. So one of the most commonly used extrapolation procedure is the Larson-Miller parameter m, which is defined as T times C plus log T sub r, where T is the temperature in Kelvin and C is a constant and usually it's 20. Log T sub r is the time to failure or the rupture time, and m is the Larson-Miller parameter. How do we use the Larson-Miller parameter? Well, in most of the cases, this Larson-Miller parameter m will be plotted against the logarithm stress, just as shown here. The x-axis is the Larson-Miller parameter m, but it's in the thousands. So this is 12,000, 16,000, and 20,000, so far so on. And the stress is the log stress. Now let's use one example to see how do we use this Larson-Miller parameter to predict the creep rupture lifetime, which is the T sub r. So estimate the rupture time T sub r for S590 iron at the given temperature, 800 degrees Celsius and the given applied stress level, which is 20,000 psi. So first, let's convert the temperature from degrees Celsius to Kelvin, since in the Lassen-Miller equation, the temperature should be in Kelvin, in unit of Kelvin. And next, let's write down the Lassen-Miller equation one more time. M equals to temperature times C plus log T sub R. Here, C, let's take 20 for C, so that's a constant. And T we already know, so if we can find the Lassen-Miller parameter at the corresponding stress level, then we can find or can solve for TR from this Lassen-Miller parameter definition. Okay, the given stress is 20,000 psi, so it will be 20 because the stress also is 10 to the is in the thousands scale. So this is 20,000 psi, and the corresponding Lassen-Miller parameter M is 24. Substitute all the values in the equation. Temperature 20 plus log T sub R equals 24 times 10 to the third. Keep in mind, this is in the thousands scale. And now we can solve T sub R, which is 233, and the unit is hour, because based on the unit shown on this plot, the Lassen-Miller parameter is Kelvin hour. So Kelvin is the unit of the temperature, and hour is the unit of the T sub R. In this chapter, we learned different material failure types. And from that, we learned that engineering materials are not as strong as predicted by theory. So their actual strength is much lower than the theoretical strength because flaws present in all materials. And the flaws act as stress concentrators. They will cause failure at stress levels that are much lower than the theoretical values. We learned 3 different types of failures based on different temperature level and the type of the applied stress. For simple fracture, it happens under static stress and at a relatively low temperature, which is usually below the 40% of the absolute melting temperature of the material. And the fracture toughness decreases with the increasing maximum flaw size in the material, decreasing temperature, and increasing rate of loading. The second failure type is fatigue. Fatigue is caused by cyclic loading or cyclic stress. So we have 2 different types of cyclic stresses. One is the reversed and one is repeated. And also there's another one, which is the random. But we will focus on the reversed stress cycle and the repeated stress cycle. So the fatigue life decreases when the stress amplitude increases. And also the mean stress will affect the fatigue life as well. For creep, it also caused by static stress or constant stress at an elevated temperature. Usually this temperature is above 40% of the melting temperature. And time to rupture, T sub R, decreases as the temperature and the applied stress increases.